In this lesson, we're going to talk about the mystery of supermassive black holes, also known as quasars, and the question of how they got to be so very, very massive.
50 years ago, the universe was a sensible place. It was quiet, peaceful, we saw stars, we knew of the planets in our own solar system. It seemed a place that was like our own sun. The entire universe, the entire galaxy was like our own sun. But then, through new technology, we started seeing things that we didn't understand.
So the universe became very strange through the efforts of people who weren't even astronomers, people like these. Radio engineers. Astronomers didn't even want to talk to them. During the Second World War, they were engaged in military radar. This, for example, is the radar station at Dover Heights in Sydney, used for spotting potential Japanese attacks. And a whole bunch of radio engineers were working here. And what they kept discovering, this is radio engineers both here and in many other countries, sure, they were looking out for incoming bombers or ships, but they kept picking up signals that apparently came from space. They ignored them at the time, but a lot of people were very interested. Oh, it looks like there's something coming from further out here. What could it be? So after the war, in some countries, these radio engineers kept going, and they started turning the same apparatus, or new pieces of equipment they built, like this one also at Dover Heights in Sydney, to try and measure these signals from space. And over the next few decades, this whole new window in astronomy opened up. Up until then, astronomy had entirely been a matter of looking, visible light. But they'd opened up this whole new window, and they started mapping the sky.
So this is a picture of what the sky looks like with a modern radio telescope. You'll see these little dots that are littered across the sky. These are objects that are emitting powerful radio signals. But the problem is if we go out and we look with an optical telescope at these sources, well, they're not usually there, or if they are there, they're very faint. The stars and galaxies that are bright in optical light hardly show up at all in radio.
Yes, if you look at the top 1,000 brightest things in the optical, they're stars, planets, the sun, and you look at the top 1,000 brightest radio sources, there's very little overlap.
There are the planets and the sun.
Jupiter and the sun and the Milky Way galaxy are in both lists, but the vast majority of the bright radio sources are not bright optically, and vice versa. For example, I spent a lot of my time studying one particular very bright radio source, one of the 1,000 brightest radio sources in the sky. So this is a radio equivalent to like a second magnitude star. And even with modern telescopes, 8-meter telescopes, long exposure times, we point at where it's coming from and we see absolutely nothing. So it's really embarrassing. This incredibly bright radio source with the most powerful optical infrared telescopes, it's apparently coming from a blank bit of sky. The trouble back in the 1960s was that the radio telescopes back then could say there's a radio source coming from somewhere in the sky, but they had very poor angular resolution. They could tell the radio waves are coming from somewhere in this area, maybe about half a degree area on the sky, but half a degree area in the sky contains maybe 200,000 stars. So how do you know which, if any, of these 200,000 stars was actually the one the radio source was coming from? So this is a great problem, and it was addressed in the 1960s using the Parkes radio telescope.
So, in the 1950s and 60s, a group in Manchester were mapping the sky through what we call the Cambridge catalogs. And they would give radio sources names. For example, a very common one would be 3C273, for example, one of the brightest sources in the sky. That was the 273rd source in their list, the third Cambridge list. And the problem is, because we didn't know where they were, we couldn't figure out what any of these objects were. So along came the Parkes radio telescope, which was among the most powerful of the day, and a very clever idea. And the clever idea was the following. In front of this really bright radio source, 3C273, the moon was going to travel, and the moon is about a half a degree across. And so they thought to look at it, and if the moon went in front of the source, which it did when they observed it, then the source would suddenly blink out, and we know exactly where the moon is on the sky, but it's a limb, so you don't know exactly where it is, so you have to wait for it to leave, and then you get another idea, and you can put those two things together, and bingo, you can triangulate the source, which is what they did in the early 1960s.
The problem was, for Cyril Hazard, the guy who did this, was that the moon was so low on the sky that when they tilted the dish over, it would have bumped into the ground. You don't generally want to do that with a dish. However, they went out and dug a little trench around the side, which allowed the telescope to point just a little bit further over without getting broken, which allowed them to actually see when the limb of the moon went over the source, and then when the limb came out again, giving you X marks the spot and the exact position of 3C273.
So once you knew where it was, you could point a telescope, an optical telescope at it, which would typically look at a much smaller piece of sky than a radio telescope. And so the people with the largest telescope in the world, the Palomar 5 meter at Caltech, went and started scanning the skies, and they soon found the source. But the source was a mystery. It was a funny little star, and it had this little squeaky thing out the side, and it had these funny features. Its spectrum looked like nothing that had ever been seen before.
These things were given the name of quasars. That stands for quasi-stellar radio source. What that means is it looks like a star, but we're not quite sure if it is or not, hence we put quasi in to hedge our bets, and it certainly emits radio waves, hence a radio source. Let me show you a picture of one that I actually helped discover. This one here, which rejoices in the name of 2138 minus 4427.
Nice name.
Thank you. And in this image, you can see some galaxies, you can see some stars in their own galaxy. And that one doesn't look very different, say, from this one. When you measure a spectrum of that one, this is what it looks like.
So that doesn't look at all like a star like the sun. This, normally, when we see features in a spectrum, they're very narrow because atoms put out single colors, and they may get broadened a little bit because of motions. But look how broad this is. This is hundreds of nanometers wide, indicating motions of tens of thousands of kilometers per second.
And you can measure a redshift of this, as we've talked about earlier in the course. In this particular case, this line, which is a little beyond 500 nanometers, turns out to be what's called the Lyman alpha line. This is when the electron around hydrogen jumps from level 2 to level 1. And in our labs on Earth, it occurs in the ultraviolet, a wavelength of 121.6 nanometers. So it's been shifted all the way from 121 nanometers to over 500. That's 323% shift. Redshift 3.23.
So that's almost all the way across the universe. So this
Yes.
thing must be incredibly distant.
Yes, so this one gets a distance of about 12 billion light years from us.
And how bright was this?
Well, it was a fairly boring quasar, this particular one about 18th magnitude.
But 18th magnitude that far away is still incredibly bright for something being so far away. If we would look at a galaxy of a billion stars, then you would normally at that distance not be able to see it at all, even with the largest telescopes on Earth.
So we're seeing something that looks like a star, looks about as bright as a star, but is billions of times further away. Therefore, it must be billion squared times brighter to appear the same. So in the next clip, I'll take you through a calculation of just how bright these things really are, and the answer is pretty scary.